In this video, we're going to talk about acids, bases, and then acid-base neutralization reactions. There's actually three pretty common acid-base theories, and we're just going to cover one of them here. And of all the theories, it's actually the least useful, but it's the most helpful when we're looking at neutralization reactions, which is the point of this section. So Arrhenius theory. According to this theory, an acid is going to be something that when I put it in water, it's going to ionize or form a hydrogen ion. So an acid is going to form a hydrogen ion when I put it in water. So if I was to take HA, I'm just using A as a generic anion, so it could be HCl, HBr, HNO3, so hydrogen and some sort of anion. It is covalent here. The bond between hydrogen and whatever A is representing is covalent. When I put it in water, however, we're going to produce ions, hydrogen being one of them. So according to this theory, it's going to produce a hydrogen ion in aqueous solution. So if you take it, you put it in water, one of your products is H+, then we're going to consider it an acid. Again, this is just one theory, but it's the one that I want to use for neutralization reactions. So produces a hydrogen ion, H+, in aqueous solution. Our base is going to be something that when we put it in water, we're going to produce a hydroxide ion. And I'm going to use M for some sort of metal cation. And then if I'm going to dissociate to produce a hydroxide ion, I actually have to have a hydroxide ion. So according to this theory, all of our bases are going to have hydroxide in them, which is why this is a really limited theory. There's a lot of species that are basic that don't have hydroxide, ammonia being a really common one, NH3. You're not going to put NH3 in water and have it dissociate into hydroxide ions. We can get a hydroxide, but it's coming from the water, not the ammonia itself. So according to this theory, it's going to dissociate to produce hydroxide ions in aqueous solution. So if I go back up, I'm going to end up with my metal cation plus a hydroxide ion. And then all of these are aqueous. So our acid is going to ionize to form a hydroxide ion, a hydrogen ion, right? Our acid, hydrogen ion in aqueous solution. And then our base is going to form a hydroxide ion in aqueous solution. When we write an acid-base neutralization reaction, what's going to happen is the hydrogen ion from my acid is going to combine with the hydroxide ion from my base, and we're going to form a water molecule. So my acid-base neutralization reaction it's going to produce water so H2O, and then a salt. And then the salt is just going to be the cation from my base plus the anion from my acid. So if we go back up to these, it's really a double replacement reaction, right? I'm going to take the hydroxide and the hydrogen. I said those backwards from how I'm squaring them off. And I am going to form a covalent bond between them. So the hydrogen will form a covalent bond to that oxygen and we'll get water. And then we're going to take the metal cation and combine it with my anion, and that's going to give me my salt. So it is a type of double replacement reaction if you want to think about it that way. When we went through the types of reactions, we did classify it as its own type. But if it helps you to get the products, you can think about it that way. So let's just do the generic version like we were doing up above. So HA plus MOH. These are an aqueous solution. I am going to form water. Water is now going to be a pure liquid. It's not an aqueous solution, right? Water isn't in solution with water. Water is just water. So it gets an L for liquid. And then my salt, you would need to actually consult your solubility rules to see what this would look like. It's usually going to be soluble, but it could be an insoluble salt. That is possible. So for this one, let's put a little asterisk on there. You do want to consult the solubility rules. Oop, totally didn't leave enough room there for that one. Sorry, guys. Solubility rules. So a real example for us. If I was to take nitric acid is one of our strong acids. It is going to be important in this section to know those strong acids. I had said in a previous video, I gave you 7 strong acids and I said to memorize them. So you do need to have memorized them before our next exam. And let's combine it with potassium hydroxide. And the hydrogen and the hydroxide are going to form a covalent bond. So we're going to end up with water, which gets an L because it's a pure liquid. And then potassium has a +1 charge on its ion, nitrate's -1, so just one of each. So potassium nitrate. Group 1A cation, potassium, soluble. We are going to write ionic and not ionic equations for these, just like we did with our precipitation reactions. So just a couple notes first. When we're writing our ionic equation, and this is where it's going to be important to know your strong acids and your weak acids. So ionic equations, again, if it's aqueous, we are going to write it as separate with the exception of our weak acids. Weak acids, though, we're going to put an AQ after them. They are weak electrolytes, so when we write our equations, we're going to keep it together. Essentially, if it's a strong electrolyte, we're going to dissociate it, right? We're going to write it in its ion form. If it's a weak electrolyte, which is going to include our insoluble ionic compounds, our weak acids and our weak bases, we're going to keep it together in its either molecular or compound form. So write strong electrolytes in, let's just say, as ions. Strong electrolytes as ions in their ionic form. So that's going to include our soluble ionic compounds. So this is where you would look up your salt. And strong acids. We're going to do weak acids differently, so this is where it's important to make sure you know which ones are strong. And then we're going to keep weak electrolytes written as compounds, keep them together. So this includes insoluble ionic compounds, weak acids, and weak bases. I won't have you do it with a weak base, but just to be complete, I am going to include it here. So remember, the easiest way to tell if something's a weak acid is to know your strong acids. If it's not a strong acid, it's a weak acid. So soluble ionic compounds and strong acids, you're going to separate them, write them as ions. And then your weak electrolytes, insoluble ionic compounds, and weak acids, you're going to keep them together, right? These are the keep together. And these were the ones to break apart, break into ions. So let's go through an example. So our first one, let's react hydrobromic acid, HBr, and lithium hydroxide. So the same instructions that we would have had for our precipitation reactions. We're going to write our balanced chemical equation. We're going to write our ionic equation and our net ionic equation. So the first thing you should do is identify whether or not your acid is strong or weak. And HBr is one of the 7 strong ones, so it is a strong acid. I'm only going to give you examples and ask on tests and quizzes strong bases, so if I give you a base, it is going to be strong. So since this is a strong acid, when I write my ionic equation, I am going to write it as H plus and Br minus. The next thing I would do is write these as ions, just like we did with precipitation. So even though HBr is a covalent bond, I'm still going to separate it. Right? That's what happens to acids in aqueous solution, is they are going to dissociate. It is a strong electrolyte, so it's going to be completely dissociated. And then lithium has a +1 charge and hydroxide has a -1 charge. So when I write my equation, I'm going to take my hydrogen and combine it with the hydroxide. I am forming a covalent bond between them, though. That's a big deal, right? It's not hydrogen ions hanging out with hydroxide ions. I am sharing electrons, overlapping orbitals, and sharing the electrons in that overlapping region. So I am forming a covalent bond between them. And then my salt is going to be the lithium combined with the bromine. So I am thinking of it as that double replacement for getting my products. So my equation, HBr plus lithium hydroxide. We're producing water, which is a pure liquid. I do want to see that L after it. Plus lithium bromide, because lithium has a +1 charge and bromide has a -1 charge. I only need one of each. Oop, I'm jumping ahead of myself and writing ionic. I only need one of each when I put them together. You would then look at your solubility rules to see if lithium bromide is soluble or insoluble. Group 1A cation. So soluble, so it gets that AQ. You do need to balance it. Don't forget to balance it. If you balance this equation, then we write our ionic and net ionic and pay attention to everything we have, it will come out balanced. And this one already is balanced. I have one of everything. So my ionic equation, again, for my ionic, I'm going to take my strong acid, my strong base, and my strong electrolyte salt, right? My soluble ionic compound, and I'm going to separate them. Water, because it's covalently bonded, that's going to fall under my non-electrolyte rules. I'm going to keep that together. We could actually go back up here. You might want to add that in your notes even. Keep weak electrolytes written as compounds. We should say weak electrolytes and non-electrolytes. That would be important to go back and stick in there. So weak electrolytes and non-electrolytes, which in this case is going to be our water. You'll actually learn in 152 that water actually does react with water to form some ions, but it's a reaction. It's not just separating. So back to my ionic equation. HBr is a strong electrolyte, it's a strong acid, so I'm going to separate it. I have one of each. Lithium hydroxide, if you use your solubility rules, you'll find out that it's a strong electrolyte. So I'm going to separate it. These should all have AQs after them because they're all dissolved in water. Again, if it's written as an ion, it's going to be dissolved in water. The water, however, I do want that L. I will take off some points if you omit it. And then because lithium bromide, my salt is soluble, I'm going to write it in its ionic form. To get my net, I'm going to do the same thing that we did with precipitation reactions. I'm going to cross out anything that's not undergoing a chemical change, right? I'm going to get rid of my spectator ions. If it's exactly the same on the reactant side of my equation as it is on my product side, it didn't change, so it's not taking part in the reaction. It's just hanging out, balancing charge. So I have one bromide on each side, so I'm going to get rid of those, and I also have one lithium ion, so I'm going to cross those out, and then I'm just going to rewrite what's left. So hydrogen plus hydroxide forming water. So my net ionic equation. If you have a strong acid, strong base neutralization reaction, this will always be your net ionic equation. It's not always the same for the weak ones, but this will always be the net ionic equation for a strong acid, strong base neutralization reaction. So always the net ionic equation for a strong acid, strong base reaction. You may have seen it before, and you'll actually learn it this way in 152, is that hydronium ions in water, right, these are aqueous. Sorry, hydrogen ions in water, these are aqueous, actually form hydronium ions. So the hydrogen will actually bond to hydronium, to water. Wow, I'm making a mess. So H plus H2O gives me H3O plus. So you'll actually write it this way in 152, and you may have seen it this way before. This is actually better. It's a more accurate way. So if you want to write it this way, I totally support that. You don't have to though. But this is hydronium. So if what I wrote above looks different than you may have learned in the past, that's probably why. Another example for us. Let's use carbonic acid, H2CO3, and sodium hydroxide. So we're going to do the same thing. We're going to write our balanced chemical equation, our ionic equation, and then our net ionic equation. Just like before, we want to identify if this acid is strong or weak. The easiest way is to memorize those 7 strong acids if you haven't done so already. This is not one of them, so this is a weak acid. So what that means for us is when we write our ionic equation, I'm actually going to keep it as H2CO3. Even though it gets an aqueous after it, I'm going to keep it together. I am going to separate these. So I have H plus. Carbonate has a -2 charge. That was our polyatomic ion, one of the ones on the list that we needed to memorize. I know there's 2 hydrogen for every 1 carbonate. Right now, that doesn't matter. I just want to write them as in their ionic form. Sodium has a +1 charge, and then of course hydroxide with its -1 charge. So my balanced chemical equation, I have H2CO3. I'm reacting it with sodium hydroxide. That's an AQ, believe it or not. And then same sort of idea. I'm going to form water. Again, those are going to covalently bond to each other. And then my salt is going to be sodium carbonate. So water, H2O with its L for liquid. And then because sodium has a +1 charge and carbonate has a -2 charge, to make the total charge 0, right? We want our net charge to be equal to 0. I'm going to need 2 sodium for every 1 carbonate. Going through our solubility rules, sodium group 1A cation, so that's going to be aqueous. We do need to balance this one, and this is one when we were going through our types of reactions or balancing reactions, I had said to think of water as HOH, right? Even though it is covalently bonded, for balancing purposes, I'm going to think of it as a hydrogen and then an OH. So I have, where should we start? Let's start with sodium. I have 2 sodium on my product side. I only have 1 on my reactant side. So when I put a 2 in front of sodium hydroxide, that gives me 2 sodium. It also gives me 2 hydroxide. So I need to put that 2 in front of water. When I do that, that gives me 2 hydroxide. It also gives me 2 hydrogen, and H2, I have 2 hydrogen, 1 carbonate on each side. So this should be my balanced equation. My ionic, again, because my acid is weak, right? It's a weak electrolyte. I am not going to write it in ionic form. I'm going to keep it together. So H2CO3, aqueous. My base is strong. Using our solubility rules, that is going to be a strong electrolyte. I do have 2 sodium hydroxide, so 2 sodium and 2 hydroxide. Again, please don't write diatomic sodium or diatomic hydroxide ions. The 2 stays in front. I'm going to 2 water molecules. Keep that together. It's a non-electrolyte. And then Na2, I have 2 sodium, so the 2 comes in front. And then I've run out of room, so we'll stick it down here. I have 1 carbonate. Again, it's not Na2, it's 2 Na pluses. So be careful, I have 2 sodium ions. My net, we are going to remove our spectator ions, right? Things that are not undergoing a chemical change. And this time the only thing I have is sodium. I have 2 sodium on both sides. So rewriting it, we end up with carbonic acid is reacting with 2 hydroxide ions to produce 2 water molecules plus carbonate ions.